Okay, in this problem, we have a wrench being applied to a bolt. And we're going to draw this wrench handle, represent using a vector, in the xy plane, so that the bolt itself is at the origin, and the wrench handle coincides with the x-axis and points out like that. Okay, so that's the x-axis, that's the y-axis. And so again, the bolt is actually here, and over here is the end of the wrench handle. Okay, so we apply a force in the direction of 1, 2, 0 is what this problem says. So the force vector is not the vector 1, 2, 0, but it's in the direction of 1, 2, 0. So the vector 1, 2, 0, or the vector 1, 2 in the xy plane might look like something like that. But this could be a lot longer, because the force is in the direction of 1, 2, 0 doesn't mean it has the same length as 1, 2, 0. So the actual length of F, which is a force in pounds, can be a lot longer and is a scalar multiple of the vector 1, 2, 0, but it's not necessarily equal to 1, 2, 0. And then the wrench handle we call D, the vector that represents the wrench handle. And that's given by, remember from the last problem, the wrench was 10 inches long. And since we've positioned it along the x-axis, the other two components have to be 0. The I and j components have to be 0. Okay, so what we want in this problem is the magnitude of F. And we know that the torque, we're given that the torque, represented by this Greek letter tau, and the magnitude of that, represented by the double bar symbols, we know that is 420 foot-pounds, given up here in the statement of the problem. So how can we find the magnitude of F given this information? Well, first things first, since the torque is in foot-pounds and the length of our wrench, this is 10 inches long, we've got to convert. So let's convert the wrench vector to feet. So 10 divided by 12, 10 twelfths or 5/6 would be the length in feet of the wrench. And so we're applying this force to the end of the wrench. It actually would be applied over here, but we can put copies of F wherever we want, so I put my copy of F there. And remember then, by definition, that tau is equal to d cross F. The torque vector is equal to d cross F, by definition. So let's find d cross F. And let's find the magnitude of that, and then we'll set it equal to 420 to figure out what the force vector, or the magnitude of the force vector, actually is. Okay, well, let's see, what would d cross F be? D is the vector 5, 6, 0, 0. And F is, well, we don't actually know. But we do know that F is a scalar multiple of the given vector 1, 2, 0. F is a scalar multiple of this vector. So we could say F is maybe C for the scalar times the vector 1, 2, 0. And when you take this cross product, you can actually leave the C on the outside and then use your pseudo determinant with ijk up top to compute the cross product. D will be the vector in the middle, so 5, 6, 0, 0. And the vector on the bottom will be what's left from F, this scalar multiple, which is F. What's left from that when you pull the C out is 1, 2, 0. And if you take this cross product, remember, you're looking to compute. You've got three components to compute. So you got C on the outside, you've got the I component, then minus is here by definition, and then the J component, and then plus the K component. You've got three of these to compute, and they're all given by determinants of submatrices that you can obtain. Well, you can obtain the I component by crossing out corresponding column, corresponding row with I in this pseudo matrix here, and take the determinant of the remaining matrix, which is 0, 0, 2, 0. Remember how to take the determinant. You go 0 times 0, and then subtract off 0 times 2, and that's just going to be 0. So we get 0, 0 minus 0, or just 0. And then to get the J component, cross out corresponding column, corresponding row to J, and again you get 0. You get 5, 6 times 0 minus 0 times 1. So you get 0 minus 0, or just 0. The K component is the only one that gives us something that's non-zero. You get 5, 6 times 2 minus 0 times 1. And so 5, 6 times 2 minus 0, which is just 5/3. Okay. So this then is equal to C. All right, let's put the 5/3 in front. 5/3 CK. The torque vector is 5/3 times C times K. So it points straight out of the XY plane the way we've designed it, which makes sense because DF and D cross F form a right-hand system. Okay, so what? So this is our torque vector. This is, remember what this is? This is D cross F. We know the magnitude of this is 420 foot-pounds from the statement of the problem up here. Okay, so let's take the magnitude of this. It's really easy to take the magnitude of a vector with one non-zero component. So D cross F, magnitude. If you think about it real hard, you'll just get 5/3 times C. Absolute value of C technically, but we know C is positive. Okay, so what? Well, let's set that equal to what we know the magnitude of the torque is. It's 420 foot-pounds. And if you solve this little equation then that I've created for C, multiply both sides by 3/5, you end up with C is 252, which means that the vector F, not that we were asked to find it, but now doing it this way we can find it, is 252 times 1, 2, 0. And the magnitude of the force vector then, okay, when you have a positive scalar multiple of a vector that you're taking the magnitude of, you can just pull out the scalar and take the magnitude of the vector. And of course that's going to be 252 times the square root of 1 squared plus 2 squared, which is 5. So 252 root 5 is the magnitude of the force, and that's in pounds, so that's important to write down the units. There you go.